Hello there. In this video we're going to be considering arbitrary functions. So let's assume that we have some function in space. Let's assume this is the function f. And let's consider any 2 points on this line. Say the vertical intercept and say this point right here. If we were to connect these 2 points with a line and extrapolate, so this line y is equal to mx plus b is going to have some slope. This slope, m, is sometimes referred to as the average rate of change on f, and since we've chosen some particular x values that make this true, namely a and b, then we call this the average rate of change of f on the interval ab, or the slope of the secant line. In this video we're going to be discussing what the slope of this line means in terms of the actual function for which we have drawn. So let's begin by trying to get a formula for the average rate of change of a function. So if we choose this point to be a and this point to be b, then this value right here, the y value, is going to be f of a, and the y value that corresponds to x equals b is going to correspond to f of b. Now, traditionally we usually take this as the x-axis and the y-axis, but we haven't really said that f is a function of x or y or z or t, so we don't really need to specify here, but traditionally we can take it as so. So as we usually know, the slope of a line is given by y2 minus y1 over x2 minus x1. So what we're going to do is we're going to call these points, x1, y1, x2, and y2. So I'm going to call this point right here x1, y1, and I'm going to call this point here x2, y2. So we can rewrite x1, y1. So x1, y1 is equivalent to the point, so x1 is chosen to be a, and the y value at that point is going to be f of a. And x2, y2 is equivalent to writing, so the x-coordinate for x2 is going to be b, and the corresponding y value is going to be f of b. So if we plug these two expressions in to this slope equation, then we can see the slope of that line, m, is going to be equal to f of b minus f of a all over b minus a. Now, this expression has nothing to do with the line itself. We've pretty much only just chosen 2 points on the curve f and just found the slope of a line that would pass through those 2 points. So the line in yellow actually has no significance to this equation. So in general, we define the average rate of change of f on interval ab to be equal to this expression, f of b minus f of a all over b minus a. And this is what we refer to as the average rate of change of f on a comma b. So we're going to assume, without loss of generality, so assume that the value a is less than b. So in terms of the graph, let's assume b is some point in the future and a is some point in the past. So let's see if we can justify a few properties of the average rate of change. So case A, the average rate of change of f on AB is a positive number. So what type of picture would this correspond to? So we have this curve. So let's choose, say, this point and that point. So the line that would pass through them is going to be this line. So therefore the average rate of change of f on this interval, AB, would be a positive number since it's increasing. So is this function always increasing? Definitely not, because we can definitely see some area for which this function is going downwards from left to right. But of course we have 2 intervals here, namely this region and this region, for which it is actually increasing. And if you pretty much look at the percentage of increasing versus decreasing, you'll realize that this function is more increasing than decreasing on this interval. And that's pretty much what this average rate of change represents. So if the average rate of change of a function is positive, then f is mostly or dominantly increasing on the interval a comma b. So case B, let's consider the case where the average rate of change of f on AB is negative. So let's draw a picture to sort of demonstrate this idea. So let's consider the same exact function, but let's choose a couple different points. Let's choose this point and say the vertical intercept. So as we see, is this function always increasing or decreasing on this interval? No, of course not. Namely, the increasing regions are there and the decreasing region is here. And at least by this picture, you may be able to see that the function is mostly decreasing on this interval, and that is pretty much tied to the average rate of change of this function, or the slope of this green line. So we can see that if the average rate of change of f on AB is negative, then f is mostly decreasing on the interval a comma b. So case C, so we've covered the positive and the negative case. Well, what about the zero case? So let's assume if the average rate of change of f on AB is equal to 0. Then we actually have two cases for this, and I'm going to call it C1 and case C2. So case 1 is going to look like this. So let's draw a flat line. So clearly if we were to choose any 2 points on this curve, then that would be a zero slope line. So any horizontal line, as we know, has a slope of 0. So if the average rate of change of f on AB, then f could be always constant on AB, or, so here's case 3, or case 4 if you may. So let's assume we have, let's see how I want to draw this. Consider this picture. I'm going to consider this point here and this point here. I'm going to connect them with a line. So if this is the case, well, clearly it's not constant on this interval, but there's an increasing interval there and is decreasing there. And if this picture is drawn to scale, you should be able to realize that this function is pretty much balanced between increasing and decreasing. It's sort of symmetric in terms of its rate of change. So if the average rate of change is equal to 0, then f could be always constant on AB, or f could be equally balanced between increasing and decreasing behavior. Now there is an important note that I need to mention here. These conclusions are valid if and only if the function f is continuous. That is, there's no breaks. Like piecewise functions have, jumps or infinite gaps or something like that. Like if you have those issues, then you can't make these conclusions. Everything has to be pretty much met in the middle of them things. Alright, so with these things being said, let's do an example. And if you have some more rigorous background or maybe some calculus, you may be able to prove these things analytically as well. So example, suppose we have the function g of x, which is equal to x cubed minus 2x squared plus 5x plus 1. And let's consider this function on the interval minus 2 comma minus 1. And I want to figure out whether this function is, for the most part, increasing, for the most part, decreasing, or equally balanced between these 2 points. This function is definitely not a constant function on this interval, so case 3a would not be considered here. So it's either going to be mostly increasing, mostly decreasing, or balanced between the two. So the average rate of this function g on the interval -2, -1, by definition is going to be g of -1 minus g of -2 all over -1 minus -2. So I'm just going to simplify the denominator before I jump into the top. So that's going to be equal to g of -1 minus g of -2 all over -1 plus 2, that's going to be 1. And so that's just going to be equal to 1 over 1 times g of -1 minus g of -2. So let's figure out these two components. So g of -1 is going to be equal to -1 cubed minus 2 minus 1 squared plus 5 minus 1 plus 1. So that's going to be -1 minus 2 minus 5 plus 1, which is going to be equal to, so that's -3, minus 5 is -8, plus 1 is -7. So this is going to be equal to 1 times -7 minus, so what's this next part going to be? So -2. So g of -2 is going to be equal to -2 cubed minus 2 times -2 squared plus 5 times -2 plus 1. So -2 cubed is going to be -8, minus 2 squared is 4 times -2 is -8. That's going to be -10, and that's going to be plus 1. So -16 minus 10 is -26, plus 1 is going to be -25. Okay, great. So we have this going to be equal to -7 plus 25. And 25 minus 7 is going to be equal to, it's going to be 18. So let's sort of summarize what we're calculating here. So the average rate of change of g on the interval -2 -1 is equal to 18, which is a positive number. So if this is the case, then we can conclude that g is mostly increasing on the interval -2 -1. And of course, we need to make sure that the function g is continuous, and polynomials do have this property, but we'll talk about polynomials and their properties a little bit later. But keep in mind that this is going to be true for polynomials in general. And also keep in mind that just because the function is mostly increasing doesn't necessarily mean it's always decreasing. It could be always increasing on this interval, but not necessarily always. So the average rate of change, assuming that we're going from left to right or least to greatest, mostly is going to be the strongest thing we can say, unless we actually consider more subintervals, actually infinitely many of them, to sort of guarantee that it's always increasing, or consider like differential calculus to sort of verify increasing at a particular point. But for now, this is just average rate of change, just an introduction. This will come in handy a little bit later, but this is just an introduction and some theoretical concepts associated to the average rate of change of functions on a particular interval.